Is life just one big game of chance, or is there some kind of hidden logic to it all? Today, we're going to go on a journey to find the mathematical patterns that are hiding inside what looks like pure randomness.
Okay, let's just dive right in with a classic puzzle. Imagine you're a kid again, and there are 6 different little toys you can get in your favorite cereal. The question is, how many boxes do you think you'd have to buy, on average, to get the complete set? It feels kind of tricky, right? Well, stick around because by the end of this, you are going to know exactly how to solve it. But to get there, we need to start with the basics. We're going to begin our journey in a place that's probably pretty familiar to all of us: simple games of chance. Yeah, we all get this stuff intuitively. You flip a fair coin, it's a 50-50 shot you'll get heads. You roll a standard die, there's a 1 in 6 chance for any number to come up. This is the foundation probability 101. But see, simple probability only really tells us about a single event. What if we want to know the long-term story? Like, if you roll a die 1,000 times, what's the average number going to be? To answer that, we need a much more powerful tool. So let's add our very first tool to the toolkits. It's called a random variable, and it is the absolute key to turning all these unpredictable outcomes into actual numbers that we can work with. Okay, so the formal definition is this. A random variable, which we'll just call x, is just a way to assign a number to the result of some random process. Think of it like a bridge connecting the chaos of chance to the nice, orderly world of mathematics. Let's make this real with our dice roll. The random process is the physical act of rolling the die. The random variable, our x, is simply the number that ends up face up: 1, 2, 3, 4, 5, or 6. And just like that, we've turned a physical action into a clean set of numbers. All right, so now that we have a way to represent randomness with numbers, we can finally ask our big question. Over the long run, what outcome should we actually expect? And this is the magic formula. The expected value, we write it as E of x, is calculated by taking every single possible value the random variable can be, multiplying it by the probability of that value happening, and then just summing all those results up. Now, I know that formula can look a little intimidating, but the core idea behind it is actually really simple. The expected value is just the long-term average. If you could repeat an experiment an infinite number of times, this is the average result you would land on. So for our die, we just apply the formula. We multiply each vast value by its 1 in 6 probability and add it all together. The result? 3.5. Now, obviously, you can't actually roll a 3.5 on a die. But if you rolled that die forever, your average would get closer and closer and closer to it. Okay, we have our basic tools, but now it is time to unlock a genuine superpower. This is the secret that lets us solve incredibly complex problems with surprising ease. It's called the linearity of expectation. So, the crucial point is this. If you have a bunch of random variables, the expected value of their total sum is just the sum of each of their individual expected values. This might sound simple, but it's incredibly powerful because, and this is the key part, it works even if the events aren't independent of each other. It lets us break a huge, messy problem down into small, simple pieces. All right, theory's over. Let's put our new superpower to the test and see how expectation helps us understand everything from the odds at a casino to the code running on our computers. Imagine you bet $100 on red in roulette. On a European wheel, your expected return is about $97. But on an American wheel, with that extra double zero slot, your expected return drops to about $95. That tiny difference in the wheel costs you an expected $2 on every single bet. That's the power of expectation at work. Now for a real test. A deck of 52 cards is shuffled. I'm going to turn them over one by one, and before each card, you'll guess what it is. Here's the catch, though. You have no memory of what cards have already appeared. So, how many correct guesses do you expect to get on average? It seems impossibly complicated. But watch what happens when we use linearity of expectation. We can look at each of the 52 guesses as its own tiny experiment. For any single guess, you have a 1 in 52 chance of being right. So the expected value for any single guess is 1/52nd. And using our superpower, we just add the expectation for all 52 guesses together. And the answer is 1. That's it. Out of 52 guesses, you expect to get exactly 1 right. Our superpower just took a brain-melting problem and made it trivially simple. And this isn't just for games. This exact same logic is crucial in computer science. There's a class of programs called Las Vegas algorithms. They're guaranteed to give you the correct answer eventually. An expectation helps us figure out how long eventually is likely to be.
Here's a simple example. You've got a big list of numbers, half are zeros, half are ones. You need to find a 1. The algorithm just picks an element at random until it finds 1. Since the probability of success on any given try is 1/2, the expected number of tries before you find a 1 is just 2. Simple, efficient, and powered by expectation.
Okay, let's circle all the way back to where we started, our cereal box puzzle. This is a famous challenge in probability theory known as the coupon collector's problem. And we can solve it using the exact same tools we just learned.
We solve this just like the card problem, by breaking it down. We look at the expected number of boxes to get the first toy, then the expected additional boxes to get a second unique toy, and so on, all the way to the 6th. Each step gets harder. But when we used linearity of expectation to add all those steps up, we find that for 6 toys, you'd expect to buy about 15 boxes to collect them all, far more than you might have guessed.
So the crucial thing to take away is this. Expectation doesn't give you a crystal ball to predict the next coin flip. What it gives you is something far more valuable, a mathematical understanding of the average outcome over time, which is absolutely essential for making smart decisions when you're faced with uncertainty.
And that brings us to the end, so I'll just leave you with one final question. Now that you have this powerful tool for looking at randomness, what game of chance in your own world, from investments to career choices, could you start to analyze in a completely new way?